So let's go ahead and talk about kind of a reverse photoelectric effect. It would make sense that if we took some photons and ran them into a surface and ejected some electrons, that if we took some electrons and slammed them into a surface, then we should be able to produce photons. And kind of the wave theory of light did not quite support what we actually observed, so photons definitely have some particle nature. And this was actually done by the Germans about 1900 or so, and they had this accelerating voltage right over here. And what they did is they just kind of got a heater, heated it up, and some electrons hopped off of the heated cathode, and the voltage accelerated these electrons at very high speeds, and they smashed into an anode, and what they produced was actually X-rays. And there's a special name for this. Actually, it's called Bremsstrahlung, and I probably horribly mispronounced that. But kind of the key thing is not all frequencies of light were absorbed. There's going to be some minimum wavelength or some maximum frequency with which we observe this, and essentially it's going to look exactly like the photoelectric effect. And what we're going to say is we're going to say that the charge multiplied by the accelerating voltage is going to be equal to hf max, which we could also say is equal to hc over lambda min. And yes, we do technically have a work function here, but in this case we're dealing with such high energies that generally we neglect the work function. What comes off of this guy is actually going to be a range of wavelengths, and you kind of see this guy right over there, and essentially not all of the energy might go into kind of a speed, and so we're going to have kind of a most probable wavelengths kind of coming off for various accelerating voltages. So let's take X-rays just a step further, and let's talk about what happens if an X-ray runs into something, or a photon runs into something. What the wave nature of light would say is if we had a photon that's going to bump into an electron, is that the light that is scattered offwards must have the same wavelength because, well, it's a photon, it doesn't have any momentum. Or it's a wave, it doesn't have any momentum. However, what we kind of found is if we had an incident photon and an electron, then the photon can bump into the electron and impart some of its momentum and hence energy to it. And what's going to happen is less energy means a longer wavelength, and so we can have the electron run into it, and we're going to have a scattered photon with a slightly smaller wavelength. And it turns out that this wavelength is going to kind of depend on the original wavelength of the photon, so it's going to be that guy right over there. And then it's going to be Planck's constant divided by the mass, the speed of light, and it turns out 1 minus cosine of this angle that the photon scatters off at. Now, I'm sure you're asking yourself, well, if we shine an X-ray onto a metal plate and some electrons come firing off, what would happen if we cranked up the energy and shined some photons onto a metal surface? Great question. It's actually something called pair production, and we need to crank up the energy, so we need a higher frequency or a shorter wavelength than, say, an X-ray, so we're going to need a gamma ray, which has a much higher energy than an X-ray does. Essentially, I have a couple of gamma rays right over here, and they're being impacted onto a metal plate, and what's going to happen is it's going to create a pair, hence the name pair production. And what it's going to create is an electron is going to come off, and then a positron, which is essentially a positively charged electron. It's going to have the same mass as an electron, only it's going to have a positive charge and not a negative charge. And we have to have enough energy in order for this to happen, so the energy has to be 2 times the mass of an electron multiplied by c squared. So I do want to finish up by talking a little bit about how photons can behave both like waves and like particles. This is something called wave-particle duality, and essentially we can treat a wave, a photon, like a particle when it's emitted or when it's absorbed, and we're going to treat it like a wave when it's traveling from the source where it was emitted to the place where it was detected. So we can treat wave as both a wave and a particle. We just have to ask ourselves, what is it doing? So this is actually fairly complementary, and actually Niels Bohr used the symbol the yin and the yang to kind of describe that, where it just depends on what it's doing and how we look at it. So you may be thinking to yourself, well, that's kind of convenient. We can treat photons like waves or particles depending on what we're talking about, let's explain diffraction now in the sense of a photon. And we know for diffraction, if we had some light shining through a single slit, then we're going to get a diffraction pattern that's going to have a maxima right here. So a bright band, then a dark band, bright band, dark, bright, and so on and so forth. When we talk about photons or any subatomic particle, this is going to be true for electrons as well in the next chapter, it turns out that there's some fundamental uncertainty to our knowledge about them, and we can't actually know the position of a photon, so kind of a delta x, and its momentum, kind of its speed, at the same time. And the product of the uncertainty in its position, delta x, multiplied by delta p, is going to be equal to a constant. It's called h bar divided by 2. And a fellow by the name of Heisenberg came up with this uncertainty principle. Now this h bar is just simply going to be equal to Planck's constant h divided by 2 pi, and this guy just pops up so often that we just don't want to write the 2 pi's. So how does this work for diffraction? Well, something we know for diffraction is that if we took this slit and we made it more and more and more narrow, then the diffraction pattern is actually going to get wider and wider and wider and wider, at least the central band. So what we're kind of doing is we're increasing our knowledge of delta x when we lower the slit, but we're going to have photons that are kind of coming through it at all angles. And so we're going to have a photon coming through it like that, like this, and like that. And as we know delta x a lot better, it turns out that we know delta p a whole lot better, because or a whole lot worse, because delta x multiplied by delta p has got to be equal to that constant. So as we increase our knowledge of this, we have to decrease our knowledge of this. Now, Heisenberg's uncertainty principle, again, delta x multiplied by delta p has got to be equal to h bar over 2, cannot be circumvented ever. We will never be able to know both the position and the momentum of photons, or electrons, perfectly. And even if we were to say, hey, let's start with a double slit experiment and cover up one of the slits and take a look at the photons that maybe strike a plate on the back of it, well, if they only have one slit to go through, then we're simply going to see the single slit diffraction pattern. It's kind of like the photons know. And when we take a look at them when they hit the plate, we're going to kind of see them build up photon by photon, and we're going to see something that kind of looks like this, dot, 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 dot. And I know when we looked at it before, when we talked about the wave nature of light, we kind of saw that the edges were fuzzy, and that's exactly what's going on, is the photons are building up kind of one by one. So just kind of graphically, what does this look like? Again, I said we cannot simultaneously know both the position and the momentum of a photon with great precision, and if we were to graph the momentum on this axis and the position on this axis, we kind of have two regimes. We have an impossible regime where the product of delta x and delta p are smaller than h bar over 2, and then we have a large allowed regime, kind of this regime way out here, where their product is actually going to be larger than or equal to h bar over 2. And we have this line right over there. And actually, I forgot the larger than on the previous slide, so it is actually greater than or equal to h bar over 2. Now, we can also argue that the better we know the energy, the less we will know where to observe it. And so sometimes you'll see Heisenberg's uncertainty principle written as such, where it's going to be delta E times delta T has got to be larger than or equal to h bar over 2. And you can actually derive that from this uncertainty relationship right here, but I'll spare you the tedium of that. Just want to talk about the uncertainty a little bit more. Now, Heisenberg's uncertainty principle is only going to apply to quantum mechanics or atomic and subatomic particles. It's not a valid excuse to write that on a lab report that, hey, this experiment was uncertain because of Heisenberg's uncertainty principle. The macroscopic world is way too big for us to observe this. It's only going to be for things like photons, electrons, and so on and so forth. So there is no shield of nature's secrets, and I don't want you to have the notion that science is intrinsically uncertain.